Hello, as we are discussing polymer processing and recycling techniques, one of the important set of polymers that we process are thermosets and rubbers, which are cross-linked systems. And during their performance, as well as just to get to know how much is the amount of cross-linking that's present in these systems, swelling of these systems is an extremely important feature. And so in this lecture, while keeping our focus on properties of cross-linked systems, we will discuss swelling. We will look at the elements of theory, which is Flory Rehner equation, which can explain how to estimate cross-link density and how to understand how much is the amount of swelling that a cross-linked polymer undergoes in the presence of a small molecule or a solvent. And we will also end with discussion related to how does this swelling phenomena happen as a function of time, and what are the different phenomena which are required for the overall swelling phenomena to proceed. So, swelling of cross-linked polymers is involved because if we have let us say linear and branched polymers and we have small molecular systems, what happens is the small molecule will get absorbed into the polymeric system and then they interact with polymer molecule, in turn leading to segmental flexibility increase in these macromolecular systems or plasticization. This of course leads to the glass transition decrease, or it may lead to increase in the flowability or decrease in viscosity of the material, and all these features we have seen already. Eventually, if a lot more amount of solvent and small molecule is present, then what happens is the solvent molecules will basically surround the macromolecule and solubilize it. So, that implies that macromolecule now is completely surrounded by solvent molecules, and so it is called solubilized solvent macromolecule system. And so, we in the end get a polymer solution, in which case polymer and solvent are completely intermixed with each other. If it is a high concentration, some entanglements would be there, but if it is a dilute system, then polymer molecule is separate compared to another polymer molecule. And so, if we look at linear branch polymer, we end up with a solution due to the effect of solvent. But let us say if there is a favorable small molecule which interacts with a cross-linked polymer, then it will increase the segmental mobility, but because of the cross links, which are covalent bonds, the polymer molecules cannot get solubilized. So, in this case what happens is there is a cross-link point which is preventing the macromolecules from getting solubilized. So, the small molecule which comes into the overall network, it can come in and it can start plasticizing, it can start interacting with these segments and increase the segmental mobility. And because the segmental mobility is increased and solvent molecule would like to form a solvation shell around all of these macromolecules, more and more solvent starts coming in. Because of this, what happens is in the network which was earlier had a lot of flexible chains, and since flexibility is there, these cross-link point move away and you get largely stretched chains. So, now a sample which had a certain volume, because of these small molecules which have come into the polymer, it becomes swollen. And so, the small molecules cause the polymer sample to swell or increase in volume, and this is possible because of the segmental flexibility and stretching of polymeric chains. So, the two phenomena which are associated in this case are the osmotic pressure of the solvent, or the fact that the solvent is miscible in polymer, and therefore, rather than remaining as pure solvent, it would like to be in mixture with polymer, it goes inside the sample. So, therefore, solvent which was otherwise outside would prefer by osmosis to go in the polymer and form a mixture of macromolecular solvent system. So, this is one feature. However, there is a limitation to the amount of solvent that can go in because of the cross link. Once the polymer chains get completely stretched, because of swelling, they cannot swell any further, no more further stretching is possible. So, therefore, the elasticity of chain, how much can it be stretched, is the other opposing factor. So, equilibrium is reached, or the amount of solvent that can swell the polymer is decided based on interplay of these two factors. So, at equilibrium, if I start with a sample which has no solvent at all and then end up with a solvent rich polymeric swollen network, this state will be determined based on the balance of this osmotic pressure with chain elasticity. Effectively, I could say that if I indicate this osmotic pressure of solvent as pi, and if I indicate the stress which is generated in the material due to stretching of chains as sigma, then at equilibrium these two have to be equal with respect to each other. So, this is the phenomenon of swelling, where a solvent would preferentially like to mix with the polymer, therefore, it comes in, but chain can stretch only so much, so it cannot keep on coming in. So, there is an equilibrium reached where the stretched chains, the stress felt by them is equal to the osmotic pressure which is due to the ingress of solvent molecules in the polymer system. So, this can be looked at by looking at the phenomena of both osmotic pressure on one hand and chain elasticity on the other. Why is this very important? Because swelling is a common phenomena from a performance point of view as well as characterization point of view. So, you can super absorbent materials which are part of sanitary napkins, diapers, they are also used in agriculture to retain the moisture in the soil. So, there are a lot of places where super absorbent materials are very commonly used, and they swell by exchanging a solvent. In this case, it happens to be water for agricultural or water based fluids in case of medical applications and other applications such as sanitary napkins and diapers. These are aqueous systems which are being absorbed into the polymeric system. And for example, polysodium acrylate is one common material which you will see talked about a lot in these super absorbent application. Of course, if we can develop a nice theory to explain how much polymer goes in based on the crosslink density, we can then measure crosslink density. I hope all of you can think in terms of, if crosslink density is more, will more solvent come in, or if crosslink density is less, more solvent come in. So, you can just try to think of in terms of two types of network, one where the crosslink density is much less. So, therefore, the chain length between two crosslink point is very high. Or the other situation where the number of crosslink points is much more and the chain length between two crosslink point is much less. So, the question is, in which case more solvent will come in, and in which case more swelling is possible. Remember how both of these questions are one and the same. Will more solvent come in, or will more swelling be possible? More swelling is possible implies more solvent comes in. And so, I hope you can recognize that this is where swelling will be lot less, because the chains are already short and they can get stretched in with low amount of solvent, and then swelling will stop. While with low crosslink polymeric system, swelling will be much more. So, if we can develop the relation between the amount of swelling in a polymeric system to its crosslink density, we can measure crosslink density. And depending on the solvent which is being exchanged, whether it is an organic solvent, then we call it organogel. If it is a water, then it is hydrogel, or any other water based systems like salt solutions, hydrogels are used. So, let us look at the theoretical foundation based on which this idea of estimating how much is the crosslink density affecting the amount of solvent that can be absorbed. Generally, we characterize the amount of swelling by looking at something called swelling ratio, which is nothing but the weight ratio of the swollen or completely stretched polymer chains configuration, amount of polymer that has water that has gone in, or amount of solvent that has gone in with respect to the dry weight when there is no solvent or no water in the system. We could also look at it from on the volume basis and in volume basis if we look at, then the swelling ratio is just inverse of polymer concentration, because in the dry state there is only polymer, and of course in the wet state there is polymer plus solvent. So, the inverse, the polymer divided by polymer plus solvent tells us, what is the overall volume fraction of polymer in the swollen state. So, generally we can find out the osmotic pressure which is defined as the change in the free energy when we have more and more solvent come in. So, when we have this network of polymer, and osmosis basically drives these small molecules to come in. Now, what we are asking is, when an additional solvent molecule comes in, what happens to the Gibbs free energy of this mixture and how much does it change. And so, the change in Gibbs free energy with respect to the number of moles of solvents that coming in, or in other words, the change in Gibbs free energy with the number of moles of solvent that are coming in, if we estimate, then that is nothing but related to the osmotic pressure pi. So, this we can find out using Flory-Huggins theory, because it is a polymer solvent system, and Flory-Huggins theory is one way to estimate how much is the Gibbs free energy change, as we have already seen. So, we can get an expression for the osmotic pressure. Now, the other side of it, which is related to stretching of the polymer chains, we can see that whenever chain is coil like, then it can have lot of conformations possible, and entropy is very high. When we stretch the chain, then the number of conformations possible become very less, and therefore entropy goes down. So, we can find, based on these entropy changes, what is the amount of force which is required, and because the force will be nothing but the change in free energy as a function of the stretching. And so, we can evaluate the stress as a function of the amount of solvent in the system, and this is based on the ideal chain model that we have already discussed, and it is related to basically the conformational entropy changing in the polymeric system. So, in this Cp is the crosslink density, or the number of chains which are involved between crosslinks, and Vs is the molar solvent. So, swelling equilibrium implies that the osmotic pressure, which is each incremental solvent molecule coming in and changing the free energy, with the stress that is generated, which implies that chains get stretched, and therefore entropy reduces and they feel a tension because they are getting stretched. So, when these two counterbalance each other, equilibrium is reached. So, Flory Rehner expression is in fact a statement of this. So, we equate the osmotic pressure with the stress which is developed in the material, and this equation basically relates the amount of swelling which is determined by phi p with the parameters crosslink density and also the interaction parameter chi, which is exclusive for a polymer solvent system. So, knowing a solvent polymer system and its interaction parameter, we can, and if we know what is the crosslink density, we can find how much is the swelling, or we can do the problem in inverse way, where we make a polymer sample, we do not know the crosslink density, but we can measure the swelling by changing looking at the weight change that happens in the material, and therefore we can estimate the crosslink density. If we have a specific chemistry by which we know already what is the crosslink density, and we can measure the volume of solvent that has gone in, and therefore phi p, which is the volume fraction of polymer, then in fact we can also estimate the interaction parameter. So, you can see Flory Rehner equation is very important in terms of crosslink system and estimating interactions between polymer and solvent systems. When swelling ratio is very high, that implies that lot of solvent is there and very less polymer. So, therefore, volume fraction of polymer phi p will be very less than 1. Then we can use some of the approximation, the usual mathematical approximation in terms of a Taylor series for logarithm, or also When we have very small number, then power less than 1 is usually much greater than the number itself. So, using these the Flory Rehner equation reduces. So, this gives us an idea about how swelling ratio changes as a function of crosslink density. So, when crosslink density becomes higher and higher, swelling ratio reduces. They are inversely related to each other. On the other hand, look at how it is related to chi, which is the interaction parameter. When chi is more negative, interactions are more favorable. So, more and more chi being negative implies higher and higher swelling ratio. So, that means more solvent can go in because of more favorable interactions. So, using this Flory Rehner equation, therefore, we can actually do measurement of crosslink density. And so, there are standards available to measure crosslink density of thermoset and rubbers based on this theoretical basis. Now, in terms of kinetics of swelling, some of what we discussed during absorption kinetics, diffusion in polymers, all of that has to be combined together in terms of swelling, with one major difference, that swelling deformation can be extremely high. Superabsorbent polymer can absorb 8 times its own weight. So, for example, if we start with a 100 gram of sample, which is the polymer material, let us say dry powder, it can become 800 gram of swollen. So, the swelling ratio in this case is 8. So, that is the amount of solvent that can be absorbed, and that is why these are called super absorbent materials. So, absorption is happening like what we discussed earlier, diffusion is happening where water is going in or other solvent is going in, but the deformation and the polymer chains that are getting stretched is much higher in this case compared to other systems that we have discussed so far. So, when we discuss the kinetics of swelling, mass transfer, diffusion or transfer of solvent has to happen. And this need not be fixed diffusion as we had discussed earlier. Large deformations are involved because swelling ratios can be extremely high, and of course, whatever we have discussed in terms of viscoelasticity and the fact that polymer chains can relax, segmental motion is possible. So, all these three have to be combined together, and that makes the kinetics of swelling a more complex phenomenon to describe. In fact, this can be also utilized for generating different types of applications, because if you have a very thin film of polymer, and let us say if it starts swelling, what happens is some places solvent molecule can go in where swelling can happen, and some other places if swelling is not that fast, then this film can start wrinkling. So, you can achieve different types of shapes by doing swelling. And so, generating smart polymers, generating sensors, generating actuators, the swelling behavior can be extremely important. And we have already seen the example of drug delivery, where again swelling and leaching out phenomena are extremely important. So, in such all these applications, not only the amount of solvent that can come at equilibrium, the kinetics of swelling is also equally important. So, with this we will close this lecture related to swelling of polymers, and look at now the next week, where we will continue to look at the sustainability aspect in terms of looking at biodegradation in the polymeric systems. Thank you.